This is Dr. Clark, and in this video we're going to learn how to use spherical coordinates to compute triple integrals. Let's get started. So the first thing you want to know with spherical coordinates is what they are. Okay, and so here's a sort of a picture that gives you a sense. What we have is normally you have your x, y, z coordinates. So a point P, you know your x, your y, your z coordinate, that specifies the location of that point. In spherical coordinates, we're going to use rho, theta, and phi. And what those are is the following. So theta is the same theta as what you would have in cylindrical coordinates or in polar coordinates. So here's r and theta down here. That's in the xy plane. Z comes up from there. Well, rho comes out from the origin. So it is actually the distance from the origin to the point. That's what rho is. And so in some sense, if you can imagine concentric circle or concentric spheres around the origin, each of those spheres has a particular radius to it. That's the rho. The theta is the same as in polar coordinates. The phi here is the angle as measured down from the z-axis. So you can see phi is measured down from the z-axis. So you could imagine there's a whole sort of circle of points up here that would all have the same phi value for a given z value. So rho, theta, and phi. Rho is the distance from the origin. Phi measures down from the z-axis. Theta measures over to, if you sort of cast the shadow down on the xy plane, theta would be the angle in that shadow. So one of the questions you might wonder is, well, what would rho equals constant, theta equals constant, or phi equals constant, and what would those regions describe? And we'll take them one by one. So I sort of mentioned this already. Rho equals constant is a sphere. So given a particular constant, all the points at a fixed distance away from the origin gives you a sphere centered at the origin. Theta equals constant gives you a half plane. So all of the points that have the same angle theta from the x-axis, well, they're all on this ray in the xy plane. Theta equals constant gives you a ray, but then in 3 dimensions that gets extended up into a half plane. And finally, phi equals constant gives you a cone. So given an angle, say 30 degrees or pi over 6 or something measured down, that gives you an angle to a point, but it could be any direction or any theta really. And so for all the different thetas, you would get a circle. And then when you take all the different z values, you get a cone. If the phi value is bigger than pi over 2, then that cone will be down below the xy plane. If you do phi equals pi over 2, you actually just get the xy plane in its entirety. Phi less than pi over 2, you get a cone up top. Bigger than pi over 2, you get a cone down bottom. And of course, the phi's can only go up to pi. So pi would be a point down on the z-axis. So phi's only go from 0 to pi, as you can sort of imagine, from 0 down to pi. You might wonder, why would you use spherical coordinates? This is sort of a joke, but it gives you the sense that certain shapes, the bounds are all real numbers. So when we start doing integrals, you're going to find out that shapes that involve cones, planes, or spheres can actually be done very easily, the integrals at least, when we use spherical coordinates. So that's the next thing, is how do you do integrals in spherical coordinates? Well, you have some function. You want to integrate it over some region D, some solid D, and dV would be your volume element. And what you're going to do is, of course, we need dV, the volume element. That's got to turn into some expression. Well, normally this is dx dy dz, or r dz dr d theta. But in spherical coordinates, it's going to involve d rho, d phi, d theta. And it turns out that dV is equal to rho squared sine of phi, d rho, d phi, d theta. And we'll see later on why that's the case. This is the function. And then you have to take the region and specify it using spherical coordinates. And the regions we're going to choose to specify using spherical coordinates will generally have a fixed range for phis and a fixed range for thetas, and then the rows are going to be bounded between some function on the inside and function on the outside in terms of phi and theta. So we'll always get nice numbers here, and if it was the region between two spheres, we could get nice numbers here, but these could be functions sometimes. If these, I mean, there are other shapes you could describe with spherical coordinates that would have other things here, but they tend to be messy, and then why would you do a messy thing when you might just use rectangular coordinates or something? So we're going to use spherical coordinates when we have shapes that can be nicely described using spherical coordinates, like cones and spheres. So let's talk about how would you convert equations from rectangular coordinates to spherical. We already saw for cylindrical coordinates we had x equals r cosine of theta, y equals r sine of theta, z was z, and x squared plus y squared is r squared. So we want similar equations for this. And what's going to happen is, what is r is the real question. So let's go back up to this picture right here and see what is r. Well, r is this distance down here. That distance is the same, would be the same as this distance right here. That would also be r. And this would be z, this distance right here. And there's a triangle right here, and it's a right triangle. And the height is, or one of the legs is z, one of the legs is r, and one of the legs is rho. And so the Pythagorean theorem would tell you that r squared plus z squared is equal to rho squared. Of course, r squared is equal to x squared plus y squared, so it's really x squared plus y squared plus z squared equals rho squared. So there's that relationship between either x, y, and z in rho, or r and z in rho. But you can also see that there's an angle here, and so we could take the cosine of that angle. That would be adjacent over hypotenuse. So cosine of phi would be z over rho, and sine of phi would be r over rho. And so if you wanted to know what, if cosine of phi is z over rho, then z is equal to rho cosine of phi, and if sine of phi is r over rho, then r would be rho sine of phi. And so if we go back down to these equations here, wherever you see this r, you're going to have rho sine of phi. So r cosine becomes rho sine of phi cosine. Y is r sine of theta, so that's rho sine of phi sine of theta. And then z we talked about was rho cosine of phi. And then the last one, x squared plus y squared plus z squared equals rho squared, or this could be just r squared plus z squared equals rho squared. So if you understand this picture, this is the key picture to understand for spherical coordinates. If you understand that picture and that right triangle, then you can understand what these equations mean. So you don't have to memorize them, you can just understand them. And now let's talk about the volume element, the dv. So in rectangular coordinates, dv just turned out to be dx, dy, dz. In cylindrical coordinates, it was r, dz, dr, d theta. What's going on in spherical coordinates is a little harder to see, but essentially you can imagine there's a little bit of theta down here, a little d theta. There's a little bit of d rho, so change in distance from the origin, and there's a little bit of d phi right here, change in the angle phi. And so if you have a little bit of change in phi, a little bit of change in theta, and a little bit of change in rho, you get this sort of rectangular sort of shape here. And then the question is, well, what's the volume of that shape? And it turns out that the volume of that shape is roughly rho squared sine of phi d rho d phi d theta. In the limit, of course, this will shrink to be infinitesimally close to like a cube or a rectangular prism, and so that's kind of what's going on in the limit. But you can kind of see these distances here. That distance there is rho sine of phi d theta, and this distance here is rho sine of phi d theta there, and there's d rho, And so when you put those together, you get rho squared sine of phi d rho d phi d theta. All right. And then finally, sort of, one of the common questions to do these is, well, when do you do an integral in cylindrical coordinates? When do you do an integral in spherical coordinates? And it really comes down to what shapes are you using. If you have cones and spheres, then spherical coordinates are really good. Obviously, if you have circles and cylinders and that kind of thing, then you might want to use cylindrical coordinates. And some problems can be done both ways, and it's just a question of which one might work. The other thing to keep an eye on is the integral is you have your function, but then you have to also multiply it by rho squared sine of phi, and you have to do these integrals. So because you've got trig functions, sometimes the integrals become difficult, but sometimes not. So the key to use spherical coordinates is for problems where it makes sense to use spherical coordinates. That's kind of the main issue. All right. And in the next video, I'll do a couple examples, and you'll see how to do actual integral problems in spherical coordinates.